The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, welcome back to Dynamic Optimality. This is a second of two lectures, and today we're going to focus mainly on lower bounds. So last time we saw this geometric connection to binary search trees. So again, it's about, is there one best binary search tree? And we represented binary search trees, or at least the execution of those algorithms, as point sets in time space. And of course, a point set corresponded to a valid execution of a BST tree where each of these points represented which nodes got touched during an access. If and only if the point set was arbitrarily satisfied, meaning you take any 2 points in the point set, if they span a rectangle that is not just a horizontal or vertical line segment, there must be a third point somewhere inside that rectangle, which in the end implies that there's a monotone path between those 2 points. And then we saw, on the upper bound side, we saw a greedy algorithm, which was the obvious offline thing to do, which is as these points come along, as you do the accesses, the white dots, you add the necessary red dots in order to make it arbitrarily satisfied, row by row. And so that seemed like the obvious offline thing to do. Turns out it could be done online up to constant factors. I sketched that last time. And this is conjectured to be within a constant factor of optimal. We can't prove it. What I'm going to show today is our best attempts at proving this is optimal. In particular, there's something called the signed greedy algorithm, which is almost the same as greedy, but it's a lower bound, and greedy is an upper bound. So all you need to do is show these two things are within a constant factor of each other, and we're done. We're not going to get there, obviously, because we haven't solved that yet. But along the way, we're going to see tango trees, which achieve this log n competitive bound. So we think greedy is constant competitive. The best we know right now is log n. This is an improvement over red-black trees, which achieve log n. Any balanced binary search tree is within a log n factor of optimal, because it's all between constant and log n that we're trying to do. Another fun consequence of lower bounds is a particular sense in which log n is necessary for some access sequences. So I argued last time that if you take like a random access sequence, or for example, if you look at a binary search tree and you say, oh, I'll just access the thing that's deepest in the tree, there's always something that's deep in the tree of depth at least log n. And so for any binary search tree, there is an access sequence. No matter what that binary search tree does, I can choose the next access to force you to take log n per operation. What we're going to see today in these lower bounds is one access sequence that for all binary search trees, they must spend log n time. Just changing the quantifiers around. So instead of for every binary search tree there is an access sequence, there is an access sequence such that for every binary search tree you need log n time. That's something we'll get easily out of these lower bounds. So let's jump into the lower bounds, and we're going to cover, you could say, 3 different lower bounds. The independent rectangles is kind of a generic class of lower bounds. Then we're going to see 2 specific choices of these independent rectangles, which are actually older than this result. So this is sort of a modern interpretation of 2 older results and a more general result. Signed greedy is going to turn out to be the best lower bound. It's better than all the ones that we will cover, but each of them has their own uses for analysis. Each of them is going to let us analyze an algorithm that we couldn't, or that we don't otherwise know how to analyze. So let's do the independent rectangle lower bound, the sort of generic one. So these lower bounds are all going to refer to the original point set, the white dots, the accesses. The idea is you're given an access sequence, a sequence xi, x1 up to xn, and you want to know some lower bound that every binary search tree requires a certain number of accesses, a certain number of node touches for that access sequence. You know it's at least n, you want something bigger than n. We've got to at least touch the nodes that are being accessed. drop this. So I want the notion of independent rectangles, and general idea is that of dependent rectangles would be something like this. I see. So these are two rectangles. I consider them dependent because one of the corners is inside the other rectangle. But this is true no matter where the points are. So, for example, if I have, I take 2 points, they span a rectangle. If I take these 2 points, for example, they span a rectangle. This corner is inside that one, so these are considered dependent rectangles in either case. So corner here does not necessarily mean a point, any of the 4 corners. Rectangle's defined by 2 points, but it has all 4 corners. And so, in particular, independent rectangles, well, for example, they might be completely disjoint. Those are going to be independent. Something like that. It's independent. But there's some other cases you can have rectangles that look like this. Okay, so, and it doesn't matter where the points are, maybe here, 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 and here, or the other way. These are independent. And there's one other kind of special case, which maybe I'll use color to draw the other one because they're right on top of each other. So I've got a point here, and a point here. Okay, these are two rectangles defined on 3 points, so they both use this point. And if you check, it does satisfy this condition, so no corner is strictly inside the other. But we also need that the rectangles are unsatisfied. So this is saying that there's no other point even on the boundary of the rectangle. So this part says, okay, there's nothing strictly inside, but we also need that on the boundary there's no other points. So this is the only sort of situation other than reflections where you get this working out as independent. Last case is independent. All right. So this is a definition. If I give you a set of rectangles, they're independent if I was looking at pairwise, but if they're pairwise independent, they will be independent. No corner of any rectangle is strictly inside any other rectangle, and there's no points of those rectangles that are inside others. Okay. Cool. So what? Lower bound says the optimal offline binary search tree, or the optimal way to add dots to satisfy your point set, is going to be at least the size of the input, meaning the number of initial points you have, plus half the maximum number of independent rectangles. Okay, so this is a max independent set problem. In general, that's NP complete. Turns out we'll be able to at least approximate the number of independent rectangles within a constant factor by the end of class. That's going to be signed greedy. So signed greedy is going to be the best way up to constant factors to choose independent rectangles. For now, someone magically tells you what's the best way, or you just choose some reasonable, any choice of independent rectangles will be a lower bound, but you get the best lower bound by choosing the max. Okay, so we're going to prove this theorem, and then we're going to see 3 different ways to choose those independent rectangles, and we'll use them for various things. Wilbur 1, Wilbur 2, and signed greedy are going to be the 3 choices for independent rectangles. All right, to prove this theorem, we're going to change it a little bit first. and this is kind of the focus of today, is the idea of signed rectangles. If you look at the rectangles in the world spanned by 2 points, there are 2 different kinds. There's ones where there's the top right, lower left kind, and then there's the top left, lower right kind. These are positive slope or negative slope. Okay, those are the 2 kinds of rectangles. And it's helpful to think about just the positive rectangles and just the slash rectangles and just the backslash rectangles separately. So we're going to call a point set, it's a little hard to pronounce. We used to call this plus satisfied. So maybe it's easiest to pronounce it that way. The symbol formerly known as plus satisfied. If all plus rectangles that are not on a horizontal or vertical line contain another point. Okay, so a point set is arbitrarily satisfied if and only if it is plus satisfied and minus satisfied. Okay, just breaking apart that definition into 2 parts. But now we're going to look at point sets that are just plus satisfied or point sets that are just minus satisfied. And then we can look at the optimal solution if you only care about plus rectangles. So this is the smallest plus satisfied point set containing all the access points, all the given points. So we'll call that the input. Okay, opt was the smallest arbitrarily satisfied. Opt plus is you just look at plus rectangles. Okay, why are we doing this? Well, for now, we're going to do it to prove this theorem. So lemma, which was what we're actually going to prove, is if you look at this opt plus thing, it's got to be at least the size of the input. Everything has to at least contain the input, plus maximum number of independent plus rectangles. Okay, so this is what we're actually going to prove. If you want to get plus satisfied and you've got k independent plus rectangles, you need to add at least that many points, so at least 1 point per plus rectangle. If you can prove this, you prove the theorem, because this holds for minus just as well as plus by symmetry. And so you take your maximum independent set of rectangles, at least half of them are plus or at least half of them are minus. You apply this bound, and that's where you get the 1/2 here. Okay, so this is stronger, I guess, than the theorem, and this is what we're actually going to prove. And so in this world, we just are thinking about plus rectangles, which is a little weird, but it works. And the proof is going to be in 3 steps. I'm first going to give you an overview of the steps, and then we'll actually do them. So this is like a two-level proof. First thing we do, the top level, is we're going to find a rectangle in the independent set. And we're going to find a vertical line that hits only that rectangle. Okay, so we're going to have some rectangle in the independent set, and we want a vertical line stabbing it such that no other rectangle is stabbed by this vertical line. So all other rectangles, it's independent, so maybe they look something like this. Nothing like this. Not obvious that such a thing exists, but it does. Actually not that hard to find. We just need some rectangle with some line. Okay. Then, using that property, we're going to be able to find some points in that rectangle that are also in the optimal plus solution. In the rectangle crossing the line. Okay, let me get another color. So we're going to find a point on the left of the line and a point on the right of the line. And they're horizontally adjacent, meaning there's no other points between them. So that's, we know there's some point in this box, and because this is a plus box, it's got to be satisfied somehow, and I claim there's actually 2 points on either side of the line. One of them could be equal to this or this, but not both, obviously, because they're horizontally aligned. Okay. And then what we're going to do is charge the rectangle to those points. Okay, and then basically we're going to remove that rectangle and repeat. And the claim is this charging sort of only happens once per point, and therefore the number of points in the optimal solution has to be at least the number of rectangles, number of plus rectangles in the independent set. So basically this is a way of ordering the rectangles. We're going to take one that has one of these vertical lines, find 2 points that pay for that rectangle, and therefore argue that opt has to be at least the number of rectangles. So we have to argue that at least one of these points is not one of the original points, right? And that's where we're getting the input plus this. So there's lots of things to check here. Let's do them one at a time. And throughout, I'm going to assume, write that at the bottom, assume all x and y coordinates are unique. This is an idea I mentioned last time as well. If you have lots of accesses to the same key, imagine them being accesses to slightly different keys. Just skew them a little bit. And it doesn't change any of the bounds much. I won't argue that here. But at the least, think of this as just a simplifying assumption to make the proofs cleaner. OK, so how are we going to do step 1? I need to find some rectangle and some vertical line that only stabs that rectangle. And the way we're going to do that is just take the widest rectangle that just has the maximum x extent. Might be more than one, but just take one of them. Okay, so it's very wide. What this tells us is that there's no other rectangle like this. Okay, this would be independent, but it would be wider, so that's not allowed. Now we have to think about all sorts of scenarios. So we've got a point here and a point here. Could still be that we have rectangles like this. They just can't go farther to the right. Could be we have rectangles that go like this. Just can't go too far to the left. They also can't, these rectangles that are anchored in the lower left and these rectangles that are anchored in the upper right can't touch each other because then one of them would be satisfied. Right, this one's going to have a point down here. This one's going to have a point here. I guess, yeah, let's see. How would it go if they were touching? We'd have a corner. Touching is a little weird. I see. Good. This can't happen because we assume the x coordinates are distinct. Okay, so that's why I did this. is the reason. So this can't happen. And I also can't have them go like this, because then there's a corner in the strict interior of the other rectangle. Okay? Is that clear? This rectangle can't come over here, because then that would be not independent. Rectangle can't come right to the same spot, because there is no same spot. That would be 2 points on the same vertical line. And so what we must have is a picture more like this, where there's an empty region in between that's not hit by... There can be many of these rectangles. Many of these rectangles. They're independent from each other. That's like this case here. Okay, there can also be some rectangles like this. But by the same argument, these guys can't touch each other, and they can't overlap horizontally, because then one of the corners would be inside the other. Question?
So for that picture, you drew a rectangle under the one you draw line to?
This one or this one?
That one.
Yeah, this one cannot happen. Or that's what we claim. Right. So that's, you're right. So we worry about, interesting. We worry about something like this.
Sorry, why can't that happen?
Yeah, you're right. I actually drew the wrong picture. Sorry. Hitting. Yeah, I really meant line segment here. I'm sorry. Poor choice of wording. So vertical line is actually just going to go the extent of the rectangle. Something like this. Sorry. We can't forbid rectangles like this. What we can forbid are rectangles like this that also try to cross that segment. Okay, we'll see why this is enough in a moment. Sorry about that. Okay, so what I really only care about the interior of this rectangle. I'm trying to get a vertical line that only stabs this rectangle, nothing else, inside the rectangle. Sorry, poor wording. I don't care about these guys outside, because I can't say anything about them. They could be all over the place in an independent set. Claim that with it, I mean, relative to what hits this rectangle, there's stuff on the left, there's stuff on the right. There are these guys. There can also be things like this. Okay, but still remaining are these regions which are not hit by any rectangles. And that's because what I was saying, these guys can't touch each other, because then there'd be equal x coordinates. They can't overlap, because then one of them would not be independent from the other. So I get my vertical lines. I just need one, but it could be any of these. In general, if you take all, for example, if you take all of these lower left anchored rectangles and take just to the right of the rightmost one, that will be a valid choice for your line, because you can argue none of these can overlap it. Okay, so that's step one. We just take a widest rectangle. The one thing we needed to forbid was something going like this all the way across. Okay. Step two. Step two is actually pretty easy. Once you've identified this red line, you basically, inside the rectangle, you know there are some points. And I'm going to take the rightmost, and then among all the rightmost points, I'm going to take the topmost point that is to the left of the line and inside the rectangle. So let P be the topmost, leftmost point. Sorry, rightmost. That is both in the rectangle and left of the line. So this is going to be, let me erase this one, make for a little bit more room. So I'm looking at all of this region to the left of the line in the rectangle. I want to take the rightmost and then topmost point, something like this. How do I know such a point exists? Because this point is such a point. And this point is to the left of the line. So, I mean, if there's nothing else in here, that is a valid choice. But in general, we go to the right as much as possible, then we go up as much as possible. So that's a point which we will call P.
Shouldn't in the So it's
It could be on the border, it could be interior, we don't know.
when you say top, so one you said topmost, what is your topmost?
Topmost means maximum y coordinate.
Oh, okay, got it. Sorry.
So it could be up here.
Sorry,
We don't know. Yeah. First we go rightmost. Then we, among all the things in that column, we go to the topmost one. So it might be on the top, it might not be. Yeah. These are points. Sorry, this is a point in opt plus. Okay, and then Q is going to be a similar thing. It's going to be the bottommost, leftmost point in opt plus that is in the rectangle and right of the line. Not totally symmetric though. We're also going to say and not below P. Okay, so now we're looking at this upper region here. Among all the things that are not below P, should have drawn this more horizontal, and to the right of the red line, so that's up to here, I guess, I want to take the leftmost column that has any points in it, and then among those take the bottommost point in the column. I claim that's actually going to be on this line. Okay, first thing to check is that such a point exists. Such a point exists because, in particular, this is such a point. It is to the right of the line, it's above the blue line, right of the red line, in the rectangle. Okay, but I claim if we take the leftmost, bottommost one, then they must actually be aligned. Why? So if it was somewhere else, like up here, or like this point, then I claim that is an unsatisfied box. Okay, let me draw that picture. Make it a little clearer. So, something like this. So we've got our red line, and we've got this picture. This is P, and then we've got actually we don't know anything about down here. This is Q. Okay, I claim that these black regions cannot have any points in them, because by definition P was in the rightmost column, so there's nothing in this strip in between P and the red line. And it was the topmost within the column, which means there's nothing above P in the column. So that's why all the points are confined to this region over here. Similarly for Q, if you look at the things that are above or on this horizontal line, which was the blue line over there, then we know that Q is there's nothing in this strip in between because Q is leftmost, and then among leftmost it was bottommost, so there's nothing down here. So that means if these guys are not horizontally aligned, there is an unsatisfied box here. Contradiction. It's a plus box. So in opt plus, there's got to be another point, which is a contradiction. So in fact, P and Q must be horizontally aligned. So that was step 2. Finally, we get to step 3. So the idea with step 3, now we're going to do a charging argument. We want to say, okay, we want to find, basically for every independent rectangle, we want to find a point that's in opt, and therefore, that was not in the original input, and therefore then opt plus has to be at least the size of the input plus 1 per each of these plus rectangles. So the idea is the following. Because of all this setup, because we made PQ horizontally aligned, we put them in, they're inside the rectangle, and furthermore they're adjacent and they cross this vertical line. And that vertical line is not crossed by any other rectangle. When I say line, I mean line segment. There's no other rectangle that hits this red thing. Therefore, these 2 points are not going to get charged as a pair ever again. If you remove this rectangle, repeat this process, PQ is never going to get charged again. So we charge to PQ, and the pair Q never charged again. Never be charged by another rectangle because no rectangle hits hits the red thing. So no rectangle contains the segment PQ, the horizontal segment PQ. Okay, so this is almost what we want. We really want a single point which is not in the input. So we have P and Q. They're horizontally aligned. Now, if they're horizontally aligned, we know that not both of them are in the original input because all y coordinates are distinct. This is usually true because you're only accessing one point per row, per time step. So one of these might be in the input, but the other one is not. So that's the one I want to hold on to and say, okay, that's a point added to opt plus that pays for this rectangle. It's not quite so simple, though, because we might have a whole bunch of horizontally aligned things, and one rectangle charges to this one rectangle charges to this one rectangle charges to this pair. That's okay, though, because here we have 4 points. Again, one of them could be in the input. The other 3 have to be added. And so you've got 3 rectangles, 3 added points, and we're happy. Question?
Just to make an argument formal, wouldn't you want to say that only when you're saying assume that x and y are always distinct, but then
Yep.
P and Q have the same either x or y.
Right, good point. So this is distinct in the input is what I meant. Obviously, any satisfied set is not going to have this property. Yeah, good. So I want to assume x and y coordinates are only distinct in the input. Opt will not have that property, and that's why P and Q can exist and have the same y coordinate. Another question?
Does this still cover the special case where your 2 points are the points of the rectangle?
Okay, so the question is, can P and Q be the points of the rectangle? One of them can be. Like P could be here, and then another point is over here. So then that will be the segment that you're using between P and Q. Or it could be Q is here and P is over here, then that's the segment. You can't have them both equal because P and Q have to be horizontally aligned. And also because there's got to be another point in there. Yeah, so that should work. You have to check that this boundary case is still okay. But the claim is no other rectangle touches this red line even on the endpoint, and therefore no other rectangle will wholly contain P and Q. And so that means you're only charging to this pair once, and then this pair charging is okay because luckily there's 3 edges here, 4 vertices. One of the vertices we can't charge to, so there's exactly the right number of things for the edges. And we're okay. This can really happen. In fact, our favorite example of the pinwheel, if instead of doing the greedy addition, we do this addition. Oops. So these are supposed to be horizontally aligned. A little hard without a grid. So I have graph blackboard. Be great. So this is not quite satisfied. Okay, I've got to add some more points. Maybe here or something. But it has the feature that here's an independent set of rectangles. I can do this one, and this one. So this is 3 independent rectangles. As far as the white points go, they're independent rectangles. The corners are not strictly inside each other, and none of the white points satisfies any of the other rectangles. And indeed, if you applied this argument, first you take the widest rectangle, you say, okay, here's my vertical red segment. I'm going to charge to these 2 guys, this segment, And then eventually this guy will charge to this segment, and this guy will charge to this segment. And luckily there are 3 added points for exactly the 3 segments for the 3 rectangles. Okay, there had to be another point, but. So that's the lower bound. A lot of work, but in the end it says, look, just find an independent set of plus boxes, plus rectangles. That's a lower bound on opt. So now question remains, how do we find a good independent set of plus boxes? And now we'll go through the 3 different ways we know how to do it. Let's start actually with Wilbur 2. It's called Wilbur 2 because it was in a paper by Wilbur, and he has I think he called it lower bound number 1 and lower bound number 2. But for pragmatic reasons, I'm going to start with number 2. It's from 1989. So it's actually an old paper, and it was sort of lost for a long time. I don't think Wilbur wrote any other papers. And it was in SciComp, a big journal. But no one, so it's a few years after splay trees, and then sort of rediscovered in the early 2000s, and turns out to be really useful for a lot of theorems. So here's the lower bound. Again, we're looking at the input point set, no added points, just the original points. Look at every point, and look at all the points that you can see from this point downward. What does C mean? I'm interested in points that below P, that when I draw the rectangle contain no other points. Okay, so this is it's sort of like a lower envelope. It's going to look something like this. And I don't know, maybe some points like this. So all of these rectangles have to be empty. Okay, so these are the downward visible points. From P. And now, among these points, you can sort them by y-coordinate. And I want to see how many times do they cross this vertical line. So if I order them by y-coordinate. So let me add some red. So I start here, maybe I go to here. Then next one is over here, so that's a cross. Then I go over here, then I cross, then I go here, then I cross, go here, here, cross. So if I visit them in order, I want to know how many times do I cross this vertical line. This is what we call, you think of this, so this is the past of P, right? All the axis is before P. Think of this as how many times you alternate between accessing on the left of the line and accessing on the right of the line. So count number of alternations, left or right of P. And again, if we assume that no key is ever accessed more than once, then there will always be left or right, never exactly on. And then I want to sum over all points. And I claim this is a lower bound. Okay, why is it a lower bound? Essentially, I take each of these red lines that cross the P vertical line, and I turn them into a box. So there's one there, one there, one there, and one there. Claim if I do this for all P, all those boxes will be independent. All those rectangles will be independent from each other. I won't prove that formally here, but you can check it. So it's obvious for one P, because each of these has a different vertical span. If you do it for all P, all the points P, these won't conflict. So by the independent rectangle lower bound, this is a lower bound on opt, up to a factor of 2. Okay, so what? Wilbur 2 is quite interesting. For a long time, we've conjectured that it is the right answer. So conjecture. I know it's a weird lower bound to even think of. It's a very hard paper to read. Without the geometric view, it's even harder to imagine the definition of this bound. But so it's sort of an algorithm. It's a way to assign boxes. Gives you a lower bound. It's a little weird. We conjecture that it's proportional to the optimal solution. We can't prove it. We've tried many times. It's a pain to work with. But it is what it is. There's one theorem that uses it, so I want to tell you about that theorem, though I don't want to go into it in too much detail. It's a neat theorem. And it's in a paper by Iacono, 2002, and it was the first paper to revitalize the Wilbur stuff. So it's like, hey, there's this Wilbur 2 bound. We can use it to solve a new problem, which is called key-independent optimality. Briefly, the idea with key-independent optimality is, suppose you've heard about dynamic optimality. You know it's really cool because splay trees and whatnot seem to really adapt to whatever your inputs are. But suppose your inputs really don't have keys. They're just arbitrary objects labeled however, just randomly. In fact, let's assume that they are labeled randomly. Suppose the keys are generated randomly because they're meaningless. They're just arbitrary things. So you figure, oh, maybe I'll make it better and just randomize them completely. If keys are random, then dynamic opt is the same thing up to constant factors as the working set bound. That's the theorem. So this is cool because it means splay trees are actually optimal in this setting where keys are random. So this is, in expectation over the randomized keys. And the way this theorem is proved is basically you take, so what this is saying is if we take a point set, arbitrary point set, but then we re-randomize the x coordinates, leave the y coordinates as they are,